Hello. Today we're starting chapter 5, and this is on analytical trig. In chapter 4, we did lots of trigonometry that had a lot of application to it, and so we spent some time doing some labs and such. As we approach chapter 5, this is more of an analytical, more theoretical, looking at relationships between trig functions, not a lot of application. So if you liked doing the lab stuff and applying what we've learned, last chapter was for you. If not so much, you like just processes and that kind of thing, then chapter 5 is for you. And maybe you just love both, like I do. Let's start with the fundamental identities of trigonometry. We're going to spend 3 days on 5.1 because there's so many important identities. And identities are just relationships, two relationships that are equal to one another. Today, most of the ones that we've learned, or that we're going to talk about, we've learned. For instance, we have the reciprocal identities, and that's just recognizing that sine is the reciprocal of cosecant, and cosecant is the reciprocal of sine. And that works for cosine and secant, tangent, cotangent. We've already talked about those. Now notice my little sticky note here. This is going to be important for you to remember these identities. It's kind of like that unit circle that has never gone away. If you spend some time learning these right up front, the rest of the chapter is going to be so much easier for you. Here's the thing though, is we start off with some pretty simple ones, and then pretty quickly they start to snowball, and they snowball pretty fast. Always stay ahead on it. Study your identities each night. The quotient identities we really have also talked about. This is recognizing that tangent is the sine value over the cosine value. Recall that tangent is opposite over adjacent. Well, that actually comes from the sine value. I'm going to write it up here where I have a little bit more space. But the sine is opposite over hypotenuse. And if I'm going to divide that by the cosine, which is adjacent over hypotenuse, and then if I bring this up and multiply by the reciprocal, I'd have hypotenuse over adjacent. So the hypotenuses cancel, and I end up at opposite over adjacent, which is tangent. There, I just proved this identity for you. Now we could do that with all these identities. I'm not going to spend a lot of time proving the identities. We're just going to kind of accept them. Now, as we do this, it will be important to recognize that we're going to fancy up these identities a little bit, and sometimes we will be squaring them, sometimes we'll cube them. You have to understand that if you have sine squared of theta, well, like in this case, if you were to write sine squared theta, it would be equal to 1 over cosecant squared theta. So you can put those to powers and it's still going to have that same relationship. Our goal here is to use the identities from the previous page to substitute and get the expression down to a single trig function, hoping to get some things to cancel out. For instance, let's just do a few of these. The sine function. Well, sine is about as easy as it gets, but secant I'm not super familiar with. So what I would probably do with this is I'd call it sine theta, and I would replace secant with an identity. I'm going to use the reciprocal identity. I'm going to change it to 1 over cosine theta. And then since sine theta is really over 1, I could multiply straight across and end up at sine theta cosine theta. Now that doesn't necessarily look any more simplified, but if you look at your identities, look back at your reciprocal identities, look at your quotient identity, what is sine over cosine equal to? Tangent. This is really tangent theta. That's what that simplifies to. Let's try another one. Number 2. These are squared. All right, that's all right. I'll go ahead and leave my cosine squared theta. But secant squared theta, I'm going to use my reciprocal identity. I like to get it back to sines and cosines because those are the ones I'm more familiar with. But I'm going to have to square it. Oh, well, look what happens here. If I'm going to multiply, which is what I'm doing here, these cosine squared thetas are going to drop out. And all we're left with is 1. That does happen quite a bit with the identities, is everything can cancel to where you're just left with one. Let's try number 3. Okay, I've got tangent and cosecant. Now, like I said previously, if nothing jumps out at me, I usually go to sines and cosines. I'm going to look at the quotient identity for tangent, and that was what I had just written up here. Here's the quotient identity. I'm going to change that. Now, this is x instead of theta, so try to be consistent. I'm going to write that as sine x over cosine x. And it's being multiplied, so I'm going to multiply by cosecant. And I'm going to change that to 1 over sine. When you replace those with their identities, you can see you can do some reducing. And I'm left with 1 over cosine x. And that's not bad. I can live with that, but I don't love that it's a fraction, and I probably could get rid of that fraction. If you think about it, 1 over cosine is really just secant x. And then I don't even have the fraction to mess with. All right, and number 4. This one we have 3 functions. We're multiplying all of these together. When you start getting a lot of them, we tend to go sines and cosines. I'm going to write sine theta and put it over 1 times secant is the same as 1 over cosine theta times cotangent. Tangent was sine over cosine. So if I went to my reciprocal identity, I would just write it 1 over tangent, but that doesn't help me because these are in sines and cosines. I want to go to the quotient identity. That would be, instead of sine over cosine, it would be cosine over sine. And then I look to reduce anything that can. Well, these cosines can cancel. And these sines can cancel. Here we go again. Everything's gone. I'm left with 1. Kind of fun, huh? All right, so let's move on. Now notice on this one that I don't have the sticky note that says remember this. That means that these will be some that you'll need to use. You need to be familiar with them, but you can always reference back to your notes to find them. There's a lot of them here, and I don't necessarily require that you remember them all. The cofunction identities really have to do with recognizing the phase shift that happens between sine and cosine, that the only difference between them is a phase shift, and same thing with the cosecant and secant, and same thing with tangent and cotangent. So recognizing that if I take pi over 2 minus the theta, and that's the cosecant, I could just replace that whole mess with secant theta. Okay, so let's go to the odd and even identities. I always think this is kind of interesting to look at and kind of explain where this one's coming from. Did you know that if you take the sine of a negative angle, that it would be equal to the opposite of the sine of the positive angle? Let's see why. I'm going to come over here where I have a little bit of space, but it all has to do with your unit circle. If you think about it, let's throw in an angle. Let's make it be pi over 6. If I look at what the sine of a negative pi over 6, well, that's right here. And the sine value is your y, so that's your short leg. The sine value would be negative 1/2 because you're down. Which happens to be exactly the same as if I were to take sine of just a positive pi over 6. And that's my sine value is my short leg, so it's right here. And so I'm up a positive 1/2. Do you see where that's just the opposite of what the sine of the positive angle is? The signs just change. It has to do with your quadrants. Let's try a cosine one though. What happens if you take the cosine of a negative angle? Well, let me see if I can maybe erase. Oops, I can't erase, sorry. I'm just going to scribble, sorry. I'm going to get rid of those because I'm going to stick with my negative 1/2. Or I'm sorry, with my pi over 6 angle. And let's do cosine now. Cosine of a negative pi over 6 angle, that's this one down here. My cosine is my long leg. I'm square root of 3 over 2. which happens to stay the same as the cosine of a positive pi over 6. They both have the same sign because you're towards the right, and cosine has to do with your x value. So what that means here, if you look at it, it kind of has to do, if you remember when we did inverses, and it just has to do with the quadrants in general. Anytime you take the sign of a negative angle, then you're going to be going downward, which is going to make the sine value negative. Cosine doesn't matter if you go up or down because it's dealing with the x value. Tangent, those are in opposite quadrants. One of them's a positive, one's a negative, so it will change the sign on that one. Okay, just wanted that to kind of make sense in your head. Again, you don't have to have those memorized. Let's try some. So this is going to kind of be the gist of it. I'm going to give you something like the sine of pi over 2 minus x, and you just look back at your identities and say, oh, well, that's really just the cosecant of x. And if I put that over, and I look at this one and say, well, cosine of pi over 2 minus x is really just secant of x. Now, I would like to clean that up because it's a fraction and it has functions I don't really like. I'd rather they be sines and cosines or maybe a tangent. Let's look at this one. Now, I'm going to show this once, but I want you to understand kind of this process. This secant that you have on the bottom, we could turn that into a 1 over cosine. But look what happens when you do that. If I were to write that as a 1 over cosine x, and so I'm taking this cosecant and I'm dividing by a fraction, I would come up and I'd multiply by the reciprocal. I'd come up and multiply it by a cosine x over 1, or just a cosine. Which means, if you think about it, since cosine x is really equal to 1 over secant x, if you want to get secant out of your denominator, you really just have to bump it up and call it a cosine. That's what we're doing here. We're taking this secant x, and since it's the reciprocal of cosine, we could just bump it up and call it cosine. And we don't necessarily have to show a lot of work to do that. So that's what I'm going to do here. I'm just going to bump that up and call it cosine x. But likewise, I can do that with cosecant x. If I don't like cosecant x and I want to turn it into, use that reciprocal identity, I can bump it down and call it, what do you think? Sine x. That's exactly right. I'm going to get rid of that, bump it down, and call it a sine x. So what I'm left with then is cosine x over sine x. Now, I'm typically not going to show work quite this messy like that, but I just wanted to show you that process. What is cosine x over sine x? That's an identity. Looking back, you should say, oh, why, that's cotangent of x. And right there is why it's important that you know those identities. If you don't know them, then you don't recognize that right there. You don't even know to look for that. You're just like, oh, it's cosine over sine. But if you're familiar with those identities, you immediately want to switch that to a single function and don't want to leave the fraction there. Okay, let's try number 6. Cosine theta, tangent theta. Okay, this isn't any of those new ones. This looks like just the old one that we had done, the reciprocal and the quotient identities. I'm going to call that cosine theta. Put it over 1. Multiply it by tangent. Now remember, I'm trying to go to sines and cosines here so things will cancel. Tangent, if you look at your quotient identity, is sine over cosine, which works nicely. That doesn't always happen. Don't expect it always to cancel out. It doesn't always happen. And it looks like I'm left with just sine theta. Okay, number 7. Oh, we got a squared here. That's okay. Just write it sine squared theta. Put it over 1. Multiply it by, let's do some reciprocal identities. This cosecant can bump down and be called sine theta. Secant can be bumped down and be called cosine theta. And let's see if we can reduce anything then. This particular sine value is squared, but it's kind of like seeing an x squared and an x. You can still reduce it. You would just still have one sitting up on top. Same deal. I can reduce these. That's going to go away, and this is just going to become a sine theta instead of it being a sine squared theta. And then it looks like I have left sine theta over cosine theta, which is a quotient identity. Sine over cosine is tangent of theta. All right, last one of these, number 8. Okay, these are your even odd functions. Let's see if you remember. The sine of a negative angle, so think back to unit circle. If you take the sine of a negative angle, will that have the same sign, S-I-G-N, the same sign as if the angle was positive? And the answer is no. That one would be positive and one would be negative. So sine of negative x is really the equivalent of the opposite of sine of just regular x. Now, let's look at cosine. If you take the cosine of a negative angle, so this one here, is that cosine going to have the same sign or a different sign than up here? And since cosine is your x, and you're moving to the right, it'd have the same sign. So I don't care if it's a positive or negative x, it's going to have the same cosine value. And then what that can reduce to, this negative is going to stay there, but sine over cosine is just tangent. So this is going to end up a negative tangent x. Last ones. Now, I'm trying to throw in some different symbols. This is an alpha symbol on number 9. It's just another Greek letter that we use for angle measurements. Let's see how we do here. We have cosine of alpha. I'm going to leave that alone. Multiplied by cosecant alpha. Well, cosecant is the reciprocal of sine, so to get rid of cosecant, I can bump it down. Remember, it's the reciprocal, so I can bump it down and call it sine. But then I also have this cotangent theta, which I could do different things with. I'm trying to think what would make the most sense to you. I guess I'm going to bump it up and call it tangent theta, because that's the reciprocal of cotangent. So I can bump it up so it's not in the denominator. Okay, that's fine, but I actually want to do even more with that. If you don't mind, I think I would like to actually put that a little bit off to the side and just call it tangent alpha out here on the side. I'm just multiplying it. It doesn't matter. I could put it even over 1 if I wanted to, but I want you to see where I'm headed with this. Cosine alpha over sine alpha times, and tangent I would write as sine alpha cosine over cosine alpha. Do you see why I wanted that kind of separate so you could see? Oh, the sines are going to cancel, the cosines are going to cancel. You end up with 1 on that. Another way that you could have done that is right here on this cotangent. I could have not bumped it up and called it tangent. Here's what I could have done with it. I could have taken this cotangent that was in the denominator and down here rewritten it, and on either side of the sign, it doesn't really matter. I'm going to do it on the left since I have more space. But I could have just written cotangent as cosine alpha over sine alpha. And then instead of dividing by that fraction, I would bring it up here and multiply by the reciprocal. And if I multiplied by the reciprocal of this, it's really just this right here. So if that would make more sense to you, you could sure do that as well. Let's try number 10, last problem. I got 2 cosine squared x minus, and I'm going to get rid of this fraction. Since secant squared is in the denominator, I can bump it up and call it its reciprocal function and call it cosine squared x, which actually works pretty slick. These are like terms. It's a cosine squared x and a cosine squared x, so I can subtract them. Think of this one having a coefficient of a 1, if that helps. What would 2 cosine squared x minus 1 cosine squared x? And you'd have 1 cosine squared x. Though we probably wouldn't really write the 1, so I'm going to use it and just use a box and call that good. Okay. Get familiar with manipulating those fractions, because that's really what it boils down to, is working through fractions and knowing those identities. Good luck.